part 3 for titrations. And in this particular section, we are going to be looking at titrations that involve weak bases and strong acids. So, what is a weak base? A weak base includes something that does not dissociate completely, but it's a basic compound. And ammonia is the most common weak base that we interact with, and that's found in Windex, ammonia, for example. So, but we're not going to work with ammonia. We're going to work with something different that's called methylamine. And so, methylamine has a formula of CH3NH2. And what we're going to do is we're going to titrate a solution of methylamine with hydrobromic acid. Hydrobromic acid is a strong acid, and methylamine is a weak base. This is very similar to what we did with a strong base and a weak acid titration. The only difference is it's opposite in comparison because we're dealing with a weak base. So we need a Kb, all right, just like we needed a Ka for weak acid, we need a Kb for a weak base, and for methylamine is 4.4 times 10 to the negative 4. All right, so we need some concentrations and volumes for each of these. So to start this off, we're going to have 50 milliliters of 0.3 molar methylamine, and we're also going to have 0.1 molar HBr. HBr is the titrant in this case. So methylene is what will be found in the Erlenmeyer flask, and HBr will be what's found in the burette. So the first thing that I'm going to do here is I'm going to focus on how many millimoles of the methylamine we have present. So we'll take the 50 and we're going to multiply by the 0.3, and that gives me 15 millimoles of the methylamine. Now, the reason why I want to figure this out is because every titration you have to have, first of all, you have to know where the half equivalence point is. You need to know where the equivalence point is, and remember, the equivalence point is where you have equal moles of acid and base, so they titrate, they neutralize each other basically. Now, to figure that out, we know the concentration of the hydrobromic acid, and we know that we need 15 millimoles to neutralize the 15 millimoles of the CH3NH2. So, setting this up into the molarity equation, what we need to do is solve for V, the volume. This volume will be in liters, and we can convert this into milliliters, but we don't necessarily have to do that because the number of moles is actually in millimoles. So that's going to give you your milliliters. So just doing some simple algebra here, we're going to take the 15 millimoles and we're going to divide it by 0.1 molar, and that gives you 15 or 150 milliliters. So to reach the equivalence point, so this is at the equivalence point, we need 150 milliliters of the 0.1 molar HBr. Now, at the half equivalence point, we need half that volume, so we need 75 milliliters. So the first problem that we're going to work with here is we're going to add in 20 milliliters of the 0.1 molar HBr. First thing we're going to do is the stoichiometry part. We're going to react the methylamine with HBr, and you're going to form this plus the bromide. Bromide doesn't matter here. Now we're going to figure out the initial. So this is the initial here for methylamine. It's always going to be 15 millimoles. That doesn't change. What is going to change is the volume and number of millimoles of HBr. So you're going to take 20 milliliters of the HBr, multiply it by 0.1 molar, and that gives you 2 millimoles of HBr. There's nothing there to begin with for the conjugate acid, so it's 0. Now the change is going to be -2 on the left and +2 on the right. That gives you 2 millimoles of the conjugate acid. This is 0, and this leaves you with 13 millimoles of the methylamine. Now the next part here is we have to understand, since we're working with a base, we're going to have Kb. So we have an equation that we can solve for Ka, because we're going to be using Henderson-Hasselbalch's equation. So we're going to calculate Ka here from Kb. So Ka is equal to Kw divided by Kb. All right, Kw is 1 times 10 to the negative 14 divided by 4.4 times 10 to the negative 4. It's going to give me 2.27 times 10 to the minus 11. Now, the reason for doing this is so we can use Henderson-Hasselbalch's equation. You say, well, how can we do that? Because we know the concentration of the conjugate acid and the base, and so pH is equal to pKa plus the log of the base over the acid. In this case, we know the Ka. To figure out the pKa, we take the negative log, 2.27 times 10 to the minus 11, plus the log of base over acid. Our base, we had 13 millimoles, divided by the 2 millimoles of conjugate acid, and so the pH is found to be equal to 11.46 initially. This is a ratio of base over acid, and so the reason why we didn't have to figure out the concentration of the methylamine and its conjugate acid is because no matter whether you use the concentration of the millimoles, it's still a ratio, and that ratio is fixed. So you don't always have to calculate the concentrations unless you're working with a different type of problem, which is possible. So let's look at another problem. So now we're going to add in, let's see here, how much we want to add. We want to add in 35 milliliters of the 0.1 molar HBr. Same process, we go through and we figure out the stoichiometry of how much reacts and how much is left over. So the initial is 15 millimoles of this. This for the acid is 3.5 millimoles. This is 0. The change is going to be minus 3.5 and then plus 3.5. That gives me 3.5 millimoles for that part. That's a 0. And this gives me 11.5 millimoles for my methylamine. So again, we're going to use Henderson-Hasselbalch's equation because we have both base and acid present. So we take the negative log of the 2.27 times 10 to the minus 11 plus the log of the base over acid. Again, fixed ratio, so we don't have to calculate the concentrations. And we get a pH equal to 11.16. Not much change there for the simple fact that we still are in a buffer zone because we have both base and conjugate acid present. So next problem, we're going to add in 75 milliliters of the 0.1 molar HBr. Same concept. We're going to go through the stoichiometry part. Alright, so initials 15, 75 times 0.1 is 7.5. The change is going to be minus 7.5, and then plus 7.5 here. That gives me 7.5 left over there, 0, and then 7.5 left over here. Interesting. What we find is that we have equal moles of acid and base, in this case base and conjugate acid. So still use Henderson-Hausbach's equation. Plug it in. And what we're going to notice is this ratio is now equal to 1, and the log of 1 is 0. So this term cancels out. So the pH here is dependent on the value of the Ka for this acid, which is 10.64. So this is also important because this is the pKa. So at the half equivalence point, the pKa is equal to the pH of the solution. You're going to find that true with all the different buffers that involve weak acids or weak bases. So give me a second here. I'm going to add a new page here so we can work on a few more problems here. Okay, so now we are going to add in the 100 milliliters of the 0.1 molar HBr. Still continuing with the same problem. We have to do the stoichiometry. This is 15 now. This is going to be 10. Subtract 10. Subtract 10. Add 10. So we see we still have a buffer. We have a little bit of base left over. We have the conjugate acid here. So we're taking negative log of 2.27 times 10 to the minus 11 plus the log of, now it's 5 over 10. And we will get 10.34 for the pH. pH is definitely going down, but notice it's going down relatively slow because we're dealing with our buffered solution. So now we're going to add in 150 milliliters of the HBr. Okay, so as we add in the 150 milliliters of HBr, we set up the equation as we've been doing, where we have to figure out the initial, how much of the HBr is going to react and how much of the conjugate acid is going to be left over. In this particular case, we have 15 millimoles of the methylamine and 15 millimoles of the HBr. So we're at what is called the equivalence point, and these two are going to cancel each other out. They're going to be equal to 0. That means that all that's left over is the methylamine, and in this case we have 15 millimoles. So we need to figure out the molarity of it. So we have 150 milliliters of HBr along with the 50 milliliters that we started with. So that's 200 milliliters total, and we're going to take the 15 divided by that. That gives you the molarity of the conjugate acid. Since the conjugate acid is the only thing that we have left, that's going to form its own equilibrium in the solution, and the pH is dependent on how much of that is left over. So we set up the ice chart, and it's been a while, at least another video since we saw the ice chart. And the ice chart is where we're going to take the 0.075 as your initial concentration for the methylamine conjugate acid, and that's going to form an equilibrium to produce methylamine and hydrogen ions. So these two are 0, as there's nothing in the solution for right now. It's just 0. So we're going to subtract X on the methylamine side, and then we're going to add X on the right hand side. Put those together to form your equilibrium, as you see here, and then you have your equilibrium here for those two. So we're going to use this, and we're going to input this information into the equilibrium expression, which is shown to you right here. So remember, it's always products over reactants. And so we plug this information in, and we get a form that looks like this, and we solve for X. So X is equal to square root of 2.27 times 10 to the minus 11 divided by 0.075, which gives me this here. Now, before we can say that our check mark is valid, we go back up to the 5% rule that you see here. So you take 5% of the initial concentration, I get 0.00375, and so that tells me that my X is valid, so we put a check mark there. Since we know the X here, and X is equal to the concentration of hydrogen ion, we just take the negative log of your value for X, and we get 5.89. So at this equivalence point, our pH is 5.89. Now, what happens if we add in 200 milliliters of the HBr? Well, this is another problem, and this problem does something a little different than what we just saw, because now, instead of having your conjugate acid or your methylamine being present after the titration, now we have excess HBr. In this case here, we have 5 millimoles of HBr. And so, this being excess HBr, the pH is dependent on that amount. So to solve for the pH, we need to figure out the concentration of HBr first. Take the 5 millimoles divided by the 250 milliliters. That comes from 200 milliliters plus the 50 milliliters initially, and that gives me a concentration of 0.02 molar for HBr. Since HBr is a strong acid, we take the negative log of that number and we get 1.70. Now, if we were to graph this pH versus volume of HCl, what we would see is a curve that looks like this. So here in the midpoint, this is your equivalence point. Here to here represents the buffer zone. right in the middle of that is your half equivalence point. And so if you go back through the calculations, you actually can graph this pH curve based off of what we've done so far. So that's just a basic problem that involves titrating a weak base with a strong acid. Now what we're going to do, we're going to look into indicators. And so indicators are used for determining when the equivalence point takes place. And so if we look at a solution, just for example here, where titrate a solution of acetic acid and we check the midpoint, the equivalence point here. Alright, and so this equivalence point happened to be around 8.9. And we come over here and we look at our indicator chart. We say, okay, which indicator would be best used to figure out the equivalence point for acetic acid? So I need an indicator that's going to change colors around 8.9. So I can see this right here, not necessarily the best because it's more around 8.3 where it changes to green. I come down to, let's see here, phenolphthalein, and I can see that that actually changes around 8.8 to 8.9. So we would want to use phenolphthalein for our indicator. Now, phenolphthalein is a very popular indicator, and lots of labs use this. In fact, you probably have used this indicator in the lab, where you see it go from no color to a light pink. That's the stopping point. If you go over that, the equivalence point, you get a magenta or dark magenta color. You know you've gone past it. You've crossed over that equivalence point. You've over titrated, in other words. So the indicators are used to really determine where the equivalence point is. If your equivalence point happened to be what did we say we used? Let's go back and look at the previous example we worked with here. So the equivalence point for this particular problem was 5.89. So let's go to the chart here and let's look at what 5.89 would be. So 5.89 would be right in here, and as we come down we see that it looks like methyl red could be a good indicator to use, and bromocresol purple might be a good indicator to use. So alizarin also might be a good indicator because it's relatively close enough. Maybe it isn't the best one, but if you didn't have the other two, you could definitely try to use it. You know that it's close enough to where you could get a rough idea. So in this particular example, I would think that the methyl red and or bromocresol purple would both be good indicators to use. Now the ureachrome black tea, probably not. I would think that methyl red or the other one would be fine. And so that's how you would determine the indicator, is that you base it off the equivalence points, this pH. Alright, if you have any questions or anything, just let me know and I'll try to get back with you.